Hello class, this is CSE-5250, sections 2 and 60, week 8, spring 2025. Alright, so let's continue our discussion on OpenMP. Alright, so let's recap it a little bit. Alright, so OpenMP is an API that allows us to write multi-threaded programs at a higher level compared to, say, pthreads. By that, I mean we don't make parallel programs by writing in functions that would create threads and join threads after we're done. Rather, we make parallel programs by using compiler directives such as pragma omp parallel. That alone creates an entire section of parallel code where we have a group of threads being created. It's called a team, by the way, where that team works on some block of code in parallel, and at the end of that block, they join back together. If you type in pragma omp parallel by itself, it creates a team of threads whose size depends on your system, where, if for example we have this AMD Ryzen 5800X 8-core processor, 8 core 16 threads, it would create a 16 thread program. But we can customize that thread count to however many threads we want by adding a num threads clause to our code. That way we can run programs with arbitrary quantities of threads. We began our foray into looking how OpenMP works, and we started with an example program that implements the trapezoidal rule. So, if you did it the same way that we had done in pthreads, where we have for each thread a specified starting and stopping position, if you think about the trapezoid rule and how we would multi-thread it, basically we give some portion of trapezoids to each thread, and each thread calculates its own local sum of trapezoids from its own starting point to its own ending point. So a local start and local stop. And this is true for every thread. We have those local sums calculated in parallel and then added together for our final result. That entailed calculating a local A and local B, those are our stopping and ending points, for each thread using code that looks like this. And this is all fine and dandy, except we've actually been doing this rather inefficiently. Let me explain. So, we have in here a for loop, but OpenMP has the ability to parallelize a for loop. And the power with this is we don't have to write our functions like this anymore. If we just started off with a single threaded trapezoid rule program, for us to make it parallel requires very minimal code changes. All we really need is to add those pragma directives. Which ones? Well, pragma omp parallel for, of course, but for making sure our program works as expected, we would need to add several more clauses to it. So pragma omp parallel for is all it takes to parallelize a for loop, but there are some caveats. In fact, today is the day that I would like to get to the parallel for directive. By default, the for loop partitioning. Okay, so parallel for parallelizes a for loop such that that team of threads gets some portion of for loop iterations. And it's typically done by blocks. So say we have 10 threads and like 10 million loop iterations. The first thread gets the first million, the next thread gets the next million after that, the next thread gets the next million after that, and so on. And that is done automatically. Basically, all the work of writing all this code to calculate a local starting point and a local stopping point, we don't need to do that anymore. Alright, so let's take a closer look into what the parallel for loop, or rather the parallel for directive, does for us. For us, we need to imagine writing our program, our trapezoid rule program, as a single-threaded program. So it would look like this. So we would have a trap function that takes in a starting and stopping point A and B, and a quantity of trapezoids n. We also need to define our function f of x. Our main function is as follows. We declare a global result to store the area under the curve. We need two variables to store our starting and stopping endpoints. We also need an integer n for our number of trapezoids. We prompt the user the starting and stopping point and the number of trapezoids, and then we calculate the area under the curve using our trap function once again, which, oh, by the way, if we were to write it as a single-threaded function, would basically like this, with a single for loop and a single starting and stopping point. Or rather, a starting and stopping point that is the same as the one that we had entered in the prompt here. If we want to parallelize it, we make very minimal changes to our code. The thread count is something that we want to be able to toggle for our purposes of seeing how many threads affects execution of the code. So there are still some code changes. Basically, we need to add a fourth parameter to our trap function, that is our thread count, which we also have to pass in to our trap function as well. So the thread count, we get that as a command line argument when we start our program. That's parsed by strtool. That's passed into our trap function. But look at what happens next. Look at line 51. That is our parallel for loop there. Pragma OMP parallel for, with two extra clauses. The first one is the thread count, and the second one is our reduction clause. Because as we've talked about before, adding in a reduction clause obviates the need to add in a critical section for when we have a shared variable being incremented by multiple threads. Because we can recognize that as a reduction operation where we repeatedly apply, we recognize the approx variable here. That is our reduction variable. We recognize that as being a reduction variable to which we apply a reduction operation of addition, because every time the for loop goes, we add something to our prox. Therefore, we just add a reduction clause saying this is a reduction there's a reduction operation going on here, and as I said, that obviates the need to add in a critical section to our code. Once again, very minimal code changes here. As an optional addition we can add, it's this. Adding code that says thread %b has calculated x, where x is the height of the current trapezoid. So that is an optional thing we can do. That's just to show which thread is calculating what. This might not be the best place to add such code, because if we want a good approximation for the area under the curve, we will want dozens of trapezoids. Okay, so how would this look like in code? Well, let's see. I'm gonna open up a folder in my virtual machine where I am going to create a new file. New document. Let's call it Trap 5 because this is the 5th trapezoid rule program that we've written so far. Okay. You're probably getting tired of dealing with the trapezoid rule at this point, but this is probably the last time where you're gonna have to write it from scratch. Okay. What I'm gonna do is I'm gonna just write the trapezoid rule function here. Well, the whole program. So include standard io.lib. Oh, my bad. H. Include standard library.h. Include omp.h. I'm gonna save that as a file under my Parallel 4 folder. I'll call it trap5.c because this is the 5th trap. This is the 5th trap program we are writing now. I'll add the function prototypes double trap double A double B and N, where A and B are our endpoints, N is the number of trapezoids. We also have to define our f of x, double f double x. There we go. Now the main function, int main int argc character star argv. That part there won't be useful for this program because we're only using command line arguments to specify the number of threads we're using. Since this is a single threaded program, including these doesn't really do anything. So it contributes nothing to our program. In fact, it'd be probably better to omit it, except we kind of need that in our next step. So let's continue on for now. Okay, so double global result equals 0.0. Double A and B. Number of trapezoids, int n. And finally, we're going to prompt the user to enter the starting and stopping endpoints and the number of trapezoids. So I'm going to say print f There we go. And then I'm simply going to say scan f, and then in quotation marks, %lf space %lf space %d in a string. So, and then I'm going to pass in the address of A, B, and N. There we go. We're going to calculate the area. Global result plus equals trap ABN. I'm gonna print the result. And then the area under the curve is that. So I'm gonna pass in, I'm gonna need to print out the area. So there we go. and return 0 at the end. So, this is our single-threaded trapezoid rule program. Alright, we're almost done. We just need to write the code for the trap function. So, double trap, double A, double B, int n, double h, x, and approx, int I, and then we need to calculate the width of each trapezoid. And that is the difference between B and A, all divided by n. Since we're finding trapezoids between A, B, and n, no. We're finding the area under the curve approximated as trapezoids from endpoints A and B. Therefore, the width of any one trapezoid is going to be B minus A all over n. So H equals B minus A over n. Okay, let's continue. So we're gonna initialize our value for approx. We're gonna initialize this as approx equals f of A plus f of B. Then we're gonna divide that all by 2. So approx equals approx divided by 2.0. Make sure you do it as divide by 2.0 and not 2. Just to make sure you're doing that as floating point division, not integer division. Though approx is already a floating point variable, so it's probably okay. I'm just gonna do it as that, just to be absolutely sure. So, we're gonna use a for loop to add all the trapezoids between our endpoints. So, for int I equals 1 because we already added the 0th trapezoid. Kinda, sort of. But anyway, let's continue. So, for int I equals 1, I is less than n minus 1 because we already added the last trapezoid, kinda, sorta. And then I plus plus. Well, we already added the first and last trapezoid, but we kinda rearranged all the trapezoids in our summation so that when we add the first and last trapezoids, we rearranged the terms in our summation such that the first and last trapezoids are really just the heights, the left height of the first trapezoid and the right height of the last trapezoid, added together and then divided by 2. You'll have to see the previous video for details about that, but for now, we need to calculate what our current x is. So this x is going to be passed into our function for us to get the height of our next trapezoid. So x equals a plus I times h. And then we're going to say approx plus equals f of x. Then we multiply by the width of our trapezoids, our approx value. So approx equals approx times h, and return the area. There we go. Oh yeah, one last thing. We need to define our f of x. we'll just simply say double f double x return x times x. There we go. So that is our whole program. Let's compile it right now and see if it works. I'm gonna say gcc-o, and because none of this requires any parallelism at all, I'm just gonna say trap5.c. So if it works, it worked. Okay, so let's do ./trap5. But notice how I never got a segfault. That's because nowhere in my code are we calling strtool. So we don't need any command line arguments. But once again, I added them anyway because we would need them for our next part. So for now, I'm gonna enter the starting and ending points. So I'm gonna do 0, 10, and say 100 trapezoids. This should give us a very crude approximation of the area under the curve. If I press enter, we get an area of 323.5-ish units. If I do this again, using the same endpoints and 1,000 trapezoids, I get a much better approximation of the area under the curve. And if I do it again, with 0, 10, and 1,000,000 trapezoids, I get an even better approximation of the area under the curve. And in the limit, where I do this, and the number of trapezoids approaches infinity, I'll get the exact area. So that's 1,000,000,000 trapezoids. This may take some time to compute, but it's saying the area under the curve is 333 and 1/3. Or at least that's what it's converging towards, because I can't input infinity in here. It'll take forever. Anyway, so that is our single-threaded trapezoid rule program. How do we parallelize it? Well, by adding a few clauses to it and a few minimal edits to our code. So here's what that looks like. I'll make a copy of that and say trap 6. So this is the 6th iteration of our trapezoid rule program. Trust me, believe me when I say this is the last time you'll have to program this thing. Okay, so how do we parallelize our trapezoid rule program? Well, the first thing we can do is go into our trap function. Well, actually, before that, we're gonna modify our trap function so it takes in our 4th parameter. That is the thread count. So I'm gonna say int thread count. In this function call, I'm gonna pass in the thread count. But wait, we never declared what a thread count is, so I need to add that as well. So I'm gonna say int thread count, and then thread count equals strtool argv1 null 10. There we go. We're almost done. I need to update this declaration of the trap function with our thread count. So int count. Because we need the thread count for our number of threads clause, that clause tells us how many threads are we going to run our parallel section with. Because, yeah, we could just slap in pragma OMP parallel 4 by itself, but we want to be able to control the number of threads we use. Therefore, num threads thread count has to be added to that directive. Okay, so is that it? Not yet. Let's try it out first. Now we need to compile this whole program, and the compile command for this program is, if you recall from the last set of slides, that was this here. So let's compile the program. gcc dash g dash wall dash f open and p dash o, the name of the program, trap 6, and then the name of the source code file. Okay, unused variable I on line 39. It says it's unused, but we are using it. So that is a warning from the system. We are using... Oh, right. I created a variable called I in here, but then I created another variable called I in here. So really that should be for int, not for int I equals 1, but rather for I equals 1. Let's try it again. Okay, now it's working as expected. Now, if we want to run a program, /trap 6. If I do that, I get a seg fault. And that's because I need to specify the number of threads. Let's go with a simple thread count, say 10 threads. So we're gonna do this with 10 threads, and I'm gonna do, say, 1,000 trapezoids. Using the same endpoints as before, 0 to 10. The area under the curve is 320 units. Let's do it again. 0, 10, 1,000. Hey, wait a minute! The value just changed. The area under the curve just changed. That's 332. And you wanna know why this is? It's because there's a race condition in our code. And where there's race conditions, we need to have a parallel, where there's race conditions, there's a parallel section of code that requires us to have a critical section, right? Actually, no. Because, as I said, the purpose of a reduction clause is to make it easier to add in a critical section. Or rather, obviate the need to explicitly write out an entire critical section. So let's add that into our code. We recognize that approx is a reduction operator, reduction variable, because we're applying a reduction operation of addition every time we run the for loop. Every for loop iteration, we are adding something to approx. But this is something that's going to be operated on by every thread in our team. Normally, this would be done using a critical section. Let's just make it a reduction. Let's just add a reduction clause to it. So, reduction clause is as follows. I'm just going to add reduction, left parenthesis, plus sign. That's to signify that our reduction operation is addition, and then approx. There we go. That is our reduction clause added to our parallel for loop. Now, if we tried this program again, with 10 threads as before, and run it multiple times over. Oh, you know what? I forgot to compile the program. Let me fix that. Okay, there we go. Is it clear? Okay, I recompiled the program. Let me just be doubly sure. Now let's rerun the program again. 10 threads, 0 and 10 as endpoints, and 1,000 trapezoids. I get an area under the curve of 332.3354999. Let's do it again. Okay. Okay, so we are getting the right result after all. Or rather, the result we're getting is no longer changing between runs, which is what was happening previously because we had that race condition. Alright. Now, so that is it with parallelizing the trapezoid rule function. So, one thing that is also mentioned in the book is the use of a private clause that makes certain shared variables private scope, so each thread will have its own copy of the same variable. The reason why this is important is because sometimes you have code where you have a shared variable that's being shared by multiple threads. You do not want that, but instead of redeclaring the variable to be within the for loop, rather you just add a private clause that would turn that variable into a private variable. So every thread has its own copy of the same variable. No thread is accidentally overwriting and messing up with other threads' same copy of that variable. I bring this up because this might not be the best example to demonstrate the use of the private clause, because we do have a shared scope variable here in the form of x, and every thread is calculating x. It's just that just to be on the safe side, we would want that x to be a private variable. So private x. So that's gonna turn our x variable, a variable with public scope, to have private scope. Basically, this would have led to another race condition. Anyway, if we run our program again with the compile command, oh, I forgot to save my code. So if I run that again and do this, we're going to see that the program now runs the same, with the same result being returned every single time. So that's what it takes to parallelize our trap function using as minimal code edits as possible. So the point of the private clause is so we don't have to rewrite our code. The point of the reduction clause is so we don't have to rewrite our code. The point of the parallel for directive is so we don't have to write in code that would calculate a local starting and stopping point for us. All that is done by the compiler and the runtime system. So all of that is so we can be faster with getting a parallel program up and running. And that's the beauty of OpenMP. We can write an entire parallel program with very little work needed, or at least nowhere near as much work as compared to other multi-threading APIs. So as I said, the point of all of this, the point of the parallel for loop, is to parallelize our for loop without having to calculate each thread's local starting and stopping point. The point of a reduction clause is to obviate the need to add in a parallel section. The point of the private clause is to make sure that if threads are accessing a shared variable and we don't want them to, say for example, it's this variable x that's needed for calculating the current height of our trapezoid. The point of the private clause is so you don't have to do this, where you don't have to cut and paste that into here. So this would now be private scope. The point of the private clause is to avoid having to rewrite our code. All we did was add in one directive with like 2 or 3 different clauses, of course, but that's it. That's all it takes to parallelize our trapezoid rule function. Don't you find this way cleaner compared to how it was done the last time, where we would go about writing in a critical section or calculating each thread's starting and stopping point? Don't you feel this is a lot neater? I hope you do, because if you recall from pthreads, we wrote code using the rote way, and now we just wrote an entire single-threaded program, added a few directives to make it parallel, and we're done! Isn't that neat? Alright, so as neat as the parallel for directive is, with parallelizing an entire for loop, I should take this time to point out the caveats of using the parallel for directive. And here they are. Number 1. OpenMP cannot parallelize do-while loops or while loops. Number 2. OpenMP cannot parallelize for loops whose number of iterations cannot be determined. Number 3. If there's a break statement in your for loop, OpenMP cannot parallelize those kinds of for loops. The infinite loop, for example, for where there's nothing here, so it's just for left parenthesis, semicolon, semicolon, right parenthesis, OpenMP cannot parallelize that kind of for loop. This kind of for loop, where there's a break statement in the middle of our code, cannot be parallelized because we cannot determine the number of loop iterations. If we need to be able to determine the number of for loop iterations in advance so that the runtime system will know how to divide those iterations between all of our threads. OpenMP can only parallelize loops that are in canonical form. So, for index equals start, for example, for int I equals 0, I is less than end, but other valid forms exist. And then I plus plus, or plus plus I, or I plus equals increment value. All of those are legal forms for our for loop. So any combination of this in the first column, this in the second column, and this in the third column, all of those are legal forms for our for loop that OpenMP can parallelize. In short, for loops only. The start and end points, the starting and end values are defined and never change throughout the for loop's execution. Increments or decrements only occur in the increment step. So this part here. So this part is the increment step. We can only increment or decrement here. Also, no breaking out of the loop allowed. If these requirements are not met, then the compiler will reject the for loop. Linear search is a good example of a for loop that OpenMP cannot parallelize. Because linear search is basically going through an array, one element at a time, to find some element that you're looking for. You can get lucky and have it be at the very beginning, or your luck could run out and it could be at the very end of the array. No matter where it is, once you find it, you don't need to search through the rest of the array. So with linear search, once you find it, you want to break out of the loop immediately. That's not allowed if you want to try to parallelize this. In other words, linear search is not the kind of algorithm you want to parallelize using a parallel for clause. So we cannot add pragma OMP parallel for to this because it'll just give it an error. So invalid exit from OpenMP structured block. We tried to parallelize a for loop that cannot be parallelized. There are some other for loops that look like they could be parallelized but really shouldn't. If a for loop iteration requires the result of a previous for loop iteration as part of the next iteration's calculation, that is called a loop carry dependence. The Fibonacci numbers are a great example of this. And yes, I know there are ways to calculate the Fibonacci numbers without having to do it recursively, but for the sake of demonstration, we're going to do it recursively. So, the Fibonacci numbers are 1, 1, 2, 3, 5, 8, 13, and so on. The next number in the sequence is the sum of the last two numbers. So to calculate, say, the 40th Fibonacci number, you need to have calculated basically all 39 Fibonacci numbers before that. that poses a problem because if we try to parallelize this, you basically have one thread starting off with the first Fibonacci numbers, but without that information, any other threads are basically jumping the gun. So, let's say we parallelize it so that one thread gets the first 24 loop iterations and the next thread gets the next 20. So the first thread starts calculating the first 20 Fibonacci numbers. So 1, 1, 2, 3, 5, 8, 13. The next thread is going to calculate something, but it's not going to be able to access the... Okay, so the second thread is going to start at the 20th Fibonacci number because we start from 0, but it needs to know the 19th and 18th Fibonacci numbers before that. Those haven't been calculated by thread 1 just yet, if these two threads started at the same time. So ideally, this thread needs to wait until Fibonacci numbers 18 and 19 have been calculated, but without any synchronization, that second thread's just going to start adding anyway. What is it going to add? It's going to add something, and that something is going to be whatever was in memory already. So it's basically potentially adding random garbage, basically. And that is a situation where you would not want to parallelize a for loop. If you have a loop carry dependency, even if the for loop is in canonical form, you cannot parallelize it because you have a loop carry dependence. You're going to get the wrong results. The main thing is to be aware of these dependencies. Here's another for loop where we have x of I being calculated as being a plus I times x, and then y of I being exp of xi. We have a dependency here in the form of yi having its value be based off of a previous value, xi. In other words, if we did these two lines of code out of order, if we swapped lines 2 and 3, we cannot calculate yi without first calculating xi. The compiler is gonna see this and throw an error saying, I have no idea what this value is. But is that a loop carry dependence? We have a data dependence, but is it loop carried? No, it's not. Because, look at the value within the square brackets. That's I, and I. If anywhere that is I minus 1, if anywhere in those square brackets it's I minus 1, or like I minus n, that's a loop carry dependence. We cannot parallelize the for loop. But there are no such instances of like I or I minus 1. They're all the same value. Therefore, we are doing our work confined to the ith for loop iteration. Therefore, no loop carry dependency. We can parallelize this for loop just fine. Just make sure the lines of code are in the right order. So don't do yi. Don't calculate yi before calculating xi. You need xi to calculate yi. But you do not need xi or yi to calculate xi plus 1 or yi plus 1. Hey, there's that pi estimating formula again. And pretty fitting because it's Pi Day right now. As of the time recording, it's March 14th, therefore it's Pi Day. So we previously calculated the number pi using an infinite sum that looked like this. So if we wanted to write code that would calculate the number pi using that infinite sum, we would have code that looks like this. We have a for loop that would add the current term, which is going to be some term from our infinite sum. So 1, negative 1/3, positive 1/5, negative 1/7. So the ith term, or I guess the kth term, is going to be negative 1 to the kth power all over 2k plus 1. 2k plus 1, that's because we are adding odd numbers, but they are alternating signs also. So reciprocals of odd numbers whose signs are alternating. So this is what it would look like as a single-threaded program. Oh, by the way, we need to calculate this to be, it's going to be 4 times the summation. If we want to parallelize this, we can do it using a parallel for loop, because there's this weird thing where if you have an infinite sum with like positive and negative terms, the order in which you add those terms might change the result. But if we're doing a finite sum, because addition is commutative and associative, it doesn't matter the order in which we can add our terms. Therefore, a loop like this is perfectly fine to parallelize. You can write this out in your own time. I'm not going to assign this one here. All I could, because it's Pi Day and it would be really fitting for Pi Day. But really the meat and potatoes is trying out the trapezoid rule function with the parallel for directive. But yeah, this is something we could try if you so want to. The problem is, if we just wrote it like this, we're gonna get random garbage. And that's because there were loop carry dependencies in here. You wanna know what that is? If we wrote this code as is, we are actually neglecting a loop carry dependency. Look here. Factor, that is our 1 to the kth, negative 1 to our to the kth power. So that is a loop carry dependency, because every time this code in the for loop executes, the last step is to flip the sign of factor. So we have to do this in order. Therefore, by parallelizing like this, we screwed up our sum and we got the wrong value. Oops. Maybe this is something I would like to assign to you. So, make it a little bit fun and fitting for Pi Day. So, you're gonna parallelize the trapezoid rule and the pi estimating program. So, we're gonna estimate the number pi using a finite sum, but we're gonna parallelize it. Okay, so the problem with this is there is a loop carry dependency somewhere in our code, and that is the fact that every for loop iteration, we flip the sign of factor to be negative, or if it was negative already, it becomes positive again. So we do need to modify our code a little bit, and that's just so we can eliminate our loop carry dependence. And an easy way to do that is to use modular arithmetic. Look at that number k. If that is odd, then the term that we're gonna add is positive. Otherwise, that term that we're gonna add is negative. And that's just another way we can make sure we have alternating terms in our summation. So the 0th term is positive, the first term is negative, the second term is positive, the third term is negative. So we can simply say if k mod 2 equals 0, if k is an odd number and 0 is an odd number for our purposes, then the term that we're adding is positive. Otherwise, the term that we're adding is negative. So we do need to add a little bit of code modification here, just to make sure our code is working properly. Yeah, we do need to make a few minor changes to our code, but really, as far as code changes here go, this is pretty simple, really. To be absolutely sure that it's working, note that factor is declared outside of our parallel section here. Factor is a shared variable. Every thread shares the same copy of factor. To make sure we've eliminated this loop carry dependency once and for all, we add a private we add a private clause to our directive here. So we say, in addition to all of this, private factor. And there we go. If we do that, now we are calculating the correct value of pi. Neat. So, alright, so all of this code, these slides talk about how we need to make certain variables private scope. So in the trapezoid rule code here, I mentioned that this variable here is a shared scope variable because we declared it outside of the for loop. To make sure that we don't have any race conditions, add a clause private x so that every thread has a private instance of the variable x. Again, this is to prevent a race condition. Although I did not observe it as we were working with the code here, let's just add it to just be safe, okay? So yeah, that's what these slides are for, addressing the fact that there is a shared scope variable that we want to have to be private scope. Therefore, private x. But yeah, we also do have to do that to myRank. If we want to add code that has each thread printing out what value it's calculating. If we omit this line of code here on line 56, we don't need to make myRank private. Once again, we can fix that issue just by moving our code, the declaration of myRank and I, to be within the for loop, but the point of using that private clause is so we can avoid having to rewrite code. Okay, so more about loops in OpenMP. The next section is all about bubble sort. And another sorting algorithm called even-odd transposition sort. So bubble sort is a sorting algorithm that uses a nested for loop. So the question here is, what if you have nested for loops? Okay, so how does bubble sort work? Well, there are two for loops. The first for loop inspects each element in the array. The second element moves elements so that they bubble up to the top. The largest elements bubble up to the top. That's why it's called bubble sort, by the way. So the first for loop goes through the array one at a time to bubble up the largest elements to the top. The inner for loop does that bubbling up. So if the current element is larger than the element to the right of it, we do a swap. And we keep swapping until we find some other element that's even larger, and we stop swapping. But we go to the next pair of elements after that, and see if the left element is larger than the right element, and then we swap if it is. That way we have our values, the largest values, bubbling all the way up to the top. So is this the kind of for loop, or doubly nested for loop, that we want to parallelize? Let's think about it. The inner for loop compares adjacent pairs of elements and moves the larger value towards the end of the array. So that's what that bubbling up is. The outer for loop just goes through the array, one element at a time, and for each element in the array, we do that bubbling up operation. Can we parallelize the code? Well, here's the thing. Let's think about the outer for loop. The outer for loop changes the state of the array by having the largest elements bubble up to the end of the array each for loop iteration. So there's a loop carry dependency here. And that loop carry dependency is, basically we need to do this in order. That way bubble sort will work. In other words, we cannot parallelize the outer for loop because we have that loop carry dependence. But can we parallelize the inner loop? Well, the inner loop also has a sequence of sets that must be done in order. We must compare consecutive elements, element 1, element 2, element 2, element 3, element 3, element 4, element 4, element 5, element 5, element 6. We have to compare them pairwise in order from beginning to end. That's another loop carry dependency. Therefore, we cannot parallelize bubble sort. Dang it. There is another sorting algorithm. It's called odd-even transposition sort. So it is another for loop that uses three for loops, but every other for loop iteration, it switches between one of the two inner for loops. So there is an outer for loop, but there are two inner for loops, and which one is used depends on the phase. We're basically doing a swap to the left and then a swap to the right. Swap to the left, swap to the right. And we have to do this in order. The algorithm does two sets of swaps in succession. Every other element, and by every other element I mean the odd indexed elements, does a swap with the element to its left if they're out of order. Then, every other element swaps with the element to its right if they're out of order. Swap to the left, swap to the right. Swap to the left, swap to the right. We must do that swap to the left, swap to the right in order. Because if we did a swap to the left, and we did another swap to the left, think about what would happen. If we swap to the left, then there are going to be some elements, the odd indexed elements are going to perform a swap with the element to its left if they're out of order. But if we try to swap to the left again, they're already sorted, so it's pointless to do another swap to the left. If we swap to the right, there are going to be some elements out of order. If we swap to the right again, they're already going to be sorted, so swapping to the right is pointless. So, we must do this swap to the left, swap to the right, swap to the left, swap to the right, in order. Therefore, we cannot parallelize the outer for loop. But can we parallelize the inner for loops? Here's the thing. It turns out we can. So, we have, let's say we are doing the swap to the left operation. The first element, that's not to be confused with the zeroth element. The first element swaps with its partner to the left. That's going to be element 0. Element 1 swaps with element 0 if they're out of order. If we go to element 2, okay, element 2 is going to be swapping with element 3 if they're out of order. Element 4 is going to swap with element 5 if they're out of order. Here's the thing though. Does swapping element 0 and element 1 affect the results of swapping elements 2 and 3? Does that then affect the result of swapping elements 4 and 5, and then 5 and 6, and then 6 and 7? Must we do these swaps in order? If we swap elements 0 and 1, does that change the result of swapping elements 2 and 3, and 4 and 5, and 6 and 7? When we do the swap to the right, we are doing similar swaps where element 1 swaps with element 2, element 3 swaps with element 4, element 5 swaps with element 6. Does elements 1 and 2 swapping with one another affect the results of elements 3 swapping with one another? No, it doesn't. These are not loop carry dependencies. So if we can swap elements, if in the left swap phase, we can swap elements 0 and 1 without having it affect the result of swapping elements 2 and 3, nothing's stopping us from swapping elements 2 and 3 first, and then swapping elements 0 and 1. If we can do these things in any order, we can parallelize it. That's the trick I like to use with recognizing what kinds of for loops can be parallelized. If you can do these, if you can imagine somehow unfolding an entire for loop, if you can do each iteration, if you can do these iterations in any order, you can parallelize it. That's the trick that I like to use to determine which kinds of for loops can be parallelized. So for us to parallelize odd-even transposition sort, well, the simple way is to add a parallel for directive to each of the two for loops. So pragma OMP parallel for num threads thread count slash default none. That slash is to indicate that the directive continues on the next line. Default none, shared an private I temp. So we just slap that same directive onto the two for loops on the two inner for loops get the same directive because we are alternating between two different parallel for loops. So the outer loop is in charge of swap to the left or swap to the right. The inner for loops is in charge of doing those individual swaps elements 0 and 1, and then 2 and 3, and then 4 and 5, and then 6 and 7. If we're doing the left swap, if we're doing the right swap, we're swapping elements 1 and 2, then 3 and 4, then 5 and 6, then 7 and 8. And yeah, this is all fine and dandy, but think about this. What we did not talk about is the fact that if we make a team of threads, there is a little bit of overhead with creating our threads. When our main thread encounters that parallel section, it must take some time to create that team of threads, and waiting at the end also takes time. Waiting for the last thread to finish also takes time. So it takes time to fork our threads, and it takes time to join our threads. So even though this is all fine and dandy, basically what we're doing is doing a fork, swap, and then join. And then we go to the next phase where we fork, swap, and join. And then we go to the next phase where we do another fork, swap, and join. Wouldn't it be neat if instead we forked before we even enter the outer for loop, and then if we encountered these parallel for loops, we use the same team of threads each time. Because as it is, we are creating and destroying the same team of threads. If we want to speed up this program even more, let's not do that. Let's make it so that the same team of threads is used for this for loop and this for loop. So we don't have to create and destroy the same team every single time. And the key is to do it like this. We say pragma OMP parallel. Pragma OMP parallel declares a parallel block of code, but as it is, the outer for loop does not do anything with those threads. That outer for loop is actually operating as though it were still single-threaded code. So that's still running on one thread. The moment we get to either inner for loop, we now have a new directive, pragma OMP 4. Those are parallel for loops, but it's not pragma OMP parallel for, it's pragma OMP 4. So what this does is, by separating out that directive, so we have pragma OMP parallel and then pragma OMP 4 separately, we create our team of threads, and then we enter our parallel for loop. And by writing it like this, where we have pragma OMP parallel for the right before the outer for loop, and then pragma OMP 4 before the two inner for loops, when we enter the outer for loop, we fork into a team of threads, and then we perform the code inside. The code inside is only performed by one thread until we get to those parallel blocks, the pragma OMP 4. Those are parallel for loops. That's when the whole team calls into action and they run this one loop in parallel. But they don't join back with the main thread until we had left the entirety of the outer for loop. The second solution has the outer for loop execute the inner for loop. Before it does that, the fork joins into a team of threads. This team does not parallelize the outer loop, but rather this team waits for the inner for loop to execute, because the inner for loops are run in parallel. This way, we use the same team of threads throughout the whole execution of our program. The last couple slides are all about loop scheduling, and maybe I have to save that for another time, because right now I would like for me to assign to you your next programming assignment. So, your next programming assignment is... Okay, so let's talk about your homework. This is your homework 2, so this is homework 2 for OpenMP. So, you're gonna try out the Fibonacci numbers program. You're gonna write this program in C, and then you're gonna add a parallel for loop directive to this for loop here. This is to show that although this for loop is in canonical form, because of the loop carry dependency, we're gonna get the wrong results if we try to parallelize it. So that's part 0 of your homework 2. Part 1 is trying the trapezoidal rule in OpenMP with a parallel for directive. So I kind of did that already here, but what we want to do is experiment with the code a little bit. So the instructions have you write the code as single-threaded code, and then add the parallel for directive to your for loop. You will need to add a reduction clause. You will need to add a private clause just to be absolutely sure that it works. For experimentation, we're going to add a printf statement here as follows. So, here it is. Printf thread %d of %d has calculated x %f \n my rank thread count x, where my rank needs to be a integer up here. Oh, we don't assign it any value yet, but rather we're going to assign it a value here. So my rank equals OMP get thread num, and thread count was the thread count that was passed all the way up here. So this is to show that this is to demonstrate which threads are being assigned which for loop iterations. So I'm going to compile this code, and I'm going to run it with 10 threads and 20 trapezoids. So 0, 10, 20, and then we can see which threads gets which for loop iterations. So with 10 threads and 20 trapezoids, that means we have 2 for loop iterations for each thread. If I did this again, okay, so this gave us a rather inaccurate result. But I also need to do one other thing. Because my rank is a shared scope variable, I need to add this to our private class, my rank. So what that does is makes it private rank, so no thread can touch it. So no thread can mess with it, basically. So let's recompile that, and I'm going to run the program again. 0, 10, and 20 trapezoids. So now each thread is calculating some portion of the area under the curve, but we get a rather inaccurate area because we have so few trapezoids. And that's okay. We're not calculating the accuracy. We're not calculating how accurate our result is. We are just seeing whether we get the same result every single time. So if I do this again, 0, 10, 20, and yeah, we get the same result again. If I did this with, say, 7 threads, then 7 does not neatly divide into 20. 7 does not neatly divide 20. We're going to have a remainder. Really, this is to show that this thread partitioning will work even if the number of threads does not neatly divide the number of for loop iterations. So if you have 20 trapezoids, 7 does not divide 20 without a remainder, no problem. It'll still work. Okay, that one was wrong. It should be 7 threads. But I shouldn't type in 0, 10, 7. I should be typing in 0, 10, 20. Okay, there we go. So, thread 0 is calculating 3 trapezoids. Thread 1 is calculating 3 trapezoids. Thread 2 is calculating 1, 2, 3 trapezoids. Thread 3 is 1, 2, 3 trapezoids. Thread 4 is 1, 2. Thread 5 is 1, 2. Thread 6 is 1, 2. Yeah, so even if the number of trapezoids cannot be evenly divided by the number of threads, it will still partition the loop iterations regardless. So really, this is the beauty of OpenMP, being able to write parallel code at a high level without having to worry about all the nitty-gritty details that we were working with previously with OpenMP. So this is what you're doing for part 1 of your programming assignment. Part 0 was to write the Fibonacci program here, where you calculate the first 40 Fibonacci numbers using a for loop, and then try to parallelize it to see what happens. Part 1 is this. Writing the trapezoid rule using a parallel for directive. You will need to add a reduction clause. You will need to add a private clause just to be sure that everything works. And part 2 is writing the pi estimating program. The pi estimating program in OpenMP. Now, I'm not going to assign a due date for this just yet. I know you probably have midterms right now, so maybe I'll formally assign it to you next week instead. So I'll give out the instructions, but the assignment itself won't be officially given to you until next week. Okay? Okay. But if you want to walk through on part 2, here we go. I'm going to create one more document here, and that is going to be our pi estimating program. So we're just going to copy it straight from the assignment itself. It's just a matter of you adding in that parallel for directive. So we're going to calculate pi using 1000 terms in our summation. We're just going to hard code this because really the point is not to get an accurate result of pi, but to make sure that the result of pi that we get is accurate. No, we want to make sure that it's accurate every time we run it. So we're going to hard code the number of terms in our summation. So let's just call it pi.c. Okay, there we go. Now, let's compile this code to see if it runs. So, the compile command is gcc-g-world-openmp-o, the name of your executable, and the name of the source code file. There we go. Okay, there is a error in here. Unused variable. Yeah, it's unused, but I'm gonna use that in a little bit. So this is gonna be useless for now. I'm gonna run it anyway. Well, I guess you could comment it out, but I'm gonna run it anyway. So the approximated value of pi is 4, so... Okay. Let me double check this to make sure it's working. Okay, I got it bug fixed. This should not be a minus equals operation. It should be factor equals negative factor. Oh, by the way, this %.18f, that's so the value of pi approximated goes up to 18 decimal places. So that's what's going on here. So this is our single-threaded pi estimating program, but implemented way more simply compared to how we did it using pthreads a while ago. So all we gotta do to parallelize it is to add our parallel for directive. So pragma omp parallel for num threads thread count. Alright, there we go. But spoiler alert, this is not how it works. There are a few more things missing here. So I'm gonna compile it anyway, just to show what went wrong. Although it is subtle, the estimate for the value of pi changes every time we run it. So for us to fix this, we need to recognize that our sum, that is a reduction variable, upon which we are doing a reduction operation of addition. So we need to add reduction, and in parentheses, plus, colon, sum. And to really make sure that this is working, okay, even that is not enough, because this is a loop carry dependency now. So if you want to alternate the sign, we want to alternate the sign using a if statement instead. If k mod 2 equals 0, factor equals 1.0, else factor equals negative 1.0. And that's just so we alternate the sign correctly. Not as a loop carry dependency, but as a calculation that isn't a loop carry dependency. So we did need to rewrite some code here, just to really make sure it works. So let's try it again. I'll recompile the program, and then I'll run the program again. Now, notice here, it did change a little bit that one time. And that's because we still have a few more variables that must be private scope. For us to do that, we're gonna have to add the private clause private, and the factor variable should be private scope. And that should be it with getting this program to work. So now if we run this program again, I'm gonna have to recompile it, and then I'm gonna run it with 10 threads again. Now, it is still changing every single time. So, there is still a few problems with this code that are to be resolved. But, if we are still getting floating point errors in this approximation for pi, there is one note that I need to bring you over, I need to tell you right now, and that is, in the previous set of slides, I did mention something about the reduction clause. If your reduction variable is a floating point variable, your result may differ based on the number of threads you use, and that's because floating point arithmetic is not associative, so A plus B plus C and A plus B plus C may have differing results. So if you're still having rounding weirdness like this, that may be because of floating point weirdness coming up here, rather than having a race condition. So floating point weirdness probably coming up again. But that is the gist of your pi estimating program written using OpenMP. So, as I said, this is a very small program, but we parallelized it by adding this one directive, and that's it. So I want you to try this out. So this is going to be part of your next assignment. So your instructions are as follows. Try out the Fibonacci numbers program here, write out the code, and then add a parallel for directive to this for loop here. So that's part 0. Part 1 is writing the trapezoidal rule program using a parallelized for loop, so a parallel for loop. And part 2 is trying the pi estimating program using also a parallel for loop. So part 1 requires you to take 2 screenshots. Take a screenshot of the program, finding the area under a curve using 10 threads and 20 trapezoids, and then do it again, but with a different number of threads. Say 7 threads instead. And that's just to show that this loop partitioning works regardless of the number of threads in our team. Okay? So, I'm not going to formally assign this just yet, but I will assign it next week. So, with that, I'm going to end the video, and if you have any questions, feel free to email me or message me over Canvas, and we're going to take it from here and just work on this assignment for the next week. I will talk about, I guess I will have to talk a little bit more about the parallel sorting algorithm as well, but I think I'll have to save that for next week. Okay? Alright, thank you.